Ah oui. Ah oui, parce que je peux pas.
On va aller.
Quand bien on va. Ouais, mes copains à CNRS en anglais aussi. Donc on nous appelle. Ouais, après, je crois qu'il y a un moment où de toute façon, c'est un bon après elle dans les mains. Ouais. Il allait les ouais, il allait les non, non, elle va en déménage. Ouais, il allait les non, non, elle va en déménage. Ouais, il allait les non, non, elle va en déménage. Ouais, il allait les non, non, elle va en déménage. Ouais, il allait les non, non, elle va en déménage. Ouais, il allait les non, non, elle va en déménage. Ouais, ouais, il allait les non, non, elle va en déménage. Ouais, ouais, il allait les il allait les
Je vais avoir beaucoup trop chaud en fait. Je vais être obligé de quitter la veste. Ah là là. Eh oui. Je vais avoir beaucoup trop chaud en fait. Je vais être obligé de quitter la veste. Ah là là. C'est bon du coup. Eh oui. Je vais avoir beaucoup trop chaud en fait. Je vais être obligé de quitter la veste. Ah là là. C'est bon du coup. Eh oui. Je vais avoir beaucoup trop chaud en fait. Je vais être obligé de quitter la veste. Ah là là. C'est bon du coup. Eh oui. Je vais avoir beaucoup trop chaud en fait. Comme ça. Je vais être obligé de quitter la veste. Ah là là. C'est bon du coup. Eh oui. Je vais avoir beaucoup trop chaud en fait. Comme ça. Je vais être obligé de quitter la veste. Ah là là. C'est bon du coup. Eh oui.
Ça renvoie vers un lien doc, c'est ça?
Ouais. Et sur le doc, il y a le lien YouTube.
Ah ouais.
Doc, il y a le lien YouTube.
Il faut le renvoyer
à Pierre.
Je peux l'envoyer par mail.
Non mais attends, je vais le faire.
Tu vas le faire.
Mais sur le lien de la famille, enfin, il a le truc de la famille. Normalement, la famille.
Ouais.
Voilà. La fin de la boule. On l'a emmené avec la boule de
Mais vous, du coup bah ouais. Hein? Comment?
C'est le même.
Il y a le lien pour lui. C'est pas parti comme coup. Non, mais si ça marche. Par contre, je suis en train de...
le formateur, ça fait. Mais en fait, c'est
Cécile est de Saclay, et Armin est ouais, sa famille c'est le chef du département. Et moi je suis aussi dans le département. Ah oui, c'est déjà
Et voilà. Oui, voilà, ouais.
Yeah, I did. Je peux le mettre à cravate.
On va faire un test.
On se partage.
Janvier, là, comme ça.
J'ai mis la salle
On alterne.
Ça marche. Tu m'invites pas. Et il est repris sur le son du web. Ouais, c'est la salle qui.
1, 2, ouais. C'est bon. Je sais pas où je vais le faire passer.
Non mais voilà, il est là. Il est allumé si tu tapes dessus.
Ouais, non, mais. Ah, ouais. Là, c'est bon? Ouais. Je sais pas. Là.
En fait, c'est qu'il n'est pas dirigé vers.
Ouais, c'est ça. Mais sinon, j'utilise. Enfin, celui-ci, il est assez directionnel. Tiens, vas-y.
Plus, je pense. Il était court.
Ouais. Ouais. Ah, ouais. Ouais, c'est vrai que. Très bien. Ok.
Tu veux dire parce qu'il doit être sur ton PC du coup.
Non, je suis le seul.
Oui, mais c'est ton espace perso.
Ouais. Je peux.
On va pas être tout seul, tu vas avoir un
Comment? y avait peut-être Rémi, mais au final, je crois que non, il n'y est pas.
Normalement, c'est bon. Il faut que tu coupes tout ce qui est sur le PC. Tu le vois?
Alors, il y a... Ok, il y a Armin.
Katia et
Katia. Il n'y a pas Cécile.
du coup, tu as... Est-ce que je le vois là? Du coup, t'as pas ta vidéo à toi?
Comment non, c'est la salle qui diffuse.
Ok.
C'est la salle, comme ça, il y a le micro de la salle.
Et ben, je pense que s'il est pas encore connu. Si.
Bonjour tout le monde, merci d'être là. Non, ouais, je l'ai coupé. En attendant. Ouais, c'est parce que j'attends Katia.
Tu peux pas les mettre sur l'écran.
Si, j'aurais juste à faire ça.
Ok, ah oui, super.
Ouais. Parce qu'il me voit d'ici. Ouais. Oui, je vais zoomer. Ok. Ok. Armin, can you hear us? Okay, I see that you.
No, I hear you very well, Thomas.
Perfect. We are just waiting for Cécile to join.
Yes, okay, no problem.
And then we'll start. Oh, really? Okay. Okay, she just arrived. Okay, tac. Hello Cécile, est-ce que tu nous entends? Ok. Je vais couper le WebEx aussi, comme ça. Ouais, Cécile. Ok. Cécile, est-ce que tu nous entends? Pas de réponse. Tu la vois sur le WebEx? Ouais.
Oui, je la vois. Je la vois.
Ok. Pas de...
Elle est pas mute, hein, donc on va voir du son.
Ouais.
Ouais. Cécile, tu nous entends?
Ouais, ça fonctionnait
Ça marchait bien.
sur ton lien, Charles.
Ouais.
Ouais.
Voilà.
Ouais.
Voilà. Je n'avais pas d'enfant,
Ah, non? Ouais, non.
c'est pas ça. Ça, c'est Julien.
C'est lui qui l'appelle. J'ai pas...
Cécile seems to be here. I can see her at least.
Est-ce que vous m'entendez là par la visio?
Ah, yes. Ça y est. Excellent.
Ça marche.
Ouais. Est-ce que... Do you all hear me well? Still? Okay, perfect. Here, I will set that up. Ok. Ouais, ça y est. Ah oui, la caméra est là. C'est
Oh, vous n'êtes pas là pour mon plastique, je crois, mais bon, si ça vous fait plaisir de me voir sur la caméra. Well, hello everybody, bonjour. J'ai donc eu l'honneur d'être désigné président de cette soutenance de thèse de Thomas Chatagnon, intitulée Stunning Balance Recovery Strategies Following External Perturbation, a Multiscale Approach with Application to Dense Crowds. Je vais donc tout d'abord présenter rapidement le jury de soutenance de cette thèse. Thomas Robert, chargé de recherche. N'hésitez pas à vous lever et dans le public. Moi, je suis chargé de recherche à l'université Gustave Eiffel à Lyon et au laboratoire de biomécanique et de mécanique des chocs. Cécile Apper-Rolland, examinatrice, que l'on avait un petit peu attendue, donc, mais qui a fini par nous rejoindre et qui est donc directrice de recherche à IJCLab à Orsay.
Bonjour.
And now Armin Seyfried, full professor in Jülich in Germany. Hello, Armin.
Hello. Hello.
Puis nous avons parmi nous Ludovic Hoyet, examinateur, qui est chargé de co-encadrant de cette thèse, et je vais y arriver, qui est chargé de recherche à l'Inria à Rennes. On continue avec Anne-Hélène Olivier, co-encadrante aussi du travail de Thomas Chatagnon, enseignant-chercheur à l'Université de Rennes 2. Co-directeur de cette thèse, Julien Pettré, qui est donc directeur de recherche à l'Inria.
C'est Thomas à être le seul à se lever.
Et Charles Pontonnier, enseignant-chercheur à l'ENS Rennes et qui a dirigé ce travail de doctorat. Et enfin moi-même, Bruno Watier, enseignant-chercheur à l'université Paul Sabatier à Toulouse 3. Bien, donc maintenant Thomas, ça va être à toi de nous présenter ton travail. Tu as environ 45 minutes pour ta soutenance, que je crois que tu vas faire en anglais. Eh bien, nous t'écoutons, suite à quoi, tout d'abord les rapporteurs de ce travail, puis les examinateurs te poseront peut-être quelques questions s'ils en ont.
Merci beaucoup. Thank you very much for this kind introduction, and thank you to all the members of the jury for being here today. So I will present today my work, and this work is related to dense crowds. So during this work, we investigated the motion in crowds. And as you may know, motion in crowds is mainly related to social interactions. Those interactions enable us to, for instance, navigate in this environment, but it's also at the origin of different social interactions, such as group formation, for instance. However, in a particular context, physical interaction comes to play, and those interactions are associated with different kind of risk, such as discomfort, anxiety, and loss of standing balance. These risks have been seen to be associated with different types of accidents, such as fall, but also fainting and thoracic compressions. Here, in this work, we will focus on the loss of standing balance in this environment, which have been observed to lead to falls, and in particular, deadly falls. Standing balance in the context of dense crowds is very challenging. First, physical interaction may arise from all possible directions, but also the motion is limited due to physical but also social constraints. In addition, events related to dense crowds are associated with a number of factors that can lead to an even more challenging standing balance. Our purpose was to be able to add new content to model standing balance for crowd simulation and models. But to do so, we first needed to understand how standing balance would work in such context. To deal with this matter, we propose here a multiscale approach with 3 different experimental scales: the individual, then multiple individuals, and finally the crowds. By climbing up the scales, we were able to gain more ecological validity to our experiments. However, by going down to the smaller scales, we gained more control over experimental parameters, and we were able to test different factors. Before jumping to the contributions, let's first have a look to the related work. Here we would like to develop a model for standing balance in dense crowd. However, so far crowd models are lacking this information. In current models, standing balance and balance recovery is either ignored or simple with very simplistic force, such as resistive force to contacts, for instance. This is probably due to the nature of experimental data regarding crowds. There is 2 main families of experiments for crowds, the laboratory and the field experiments. However, in these 2 experimental paradigms, the motion of the individuals is depicted by a very limited number of points, such as, for instance, the head trajectory or the head and shoulders. However, those modeling could not allow the study of the full standing recovery strategies of the participants. So to deal with this matter, work has been done on smaller scales with only a limited number of participants. There's only a few studies regarding standing balance with multiple individuals, and even fewer regarding recovery strategies. There's first the so-called human domino model, which have been created by Wang and Wang. This is a collective recovery model. However, here stepping strategy and different stepping strategy are not taken into account, or stepping strategy are using very simplistic stepping rules. Then there is the work of Lee and collaborators who focused more on stepping characteristics, so stepping strategy. However, this study was only using 3 participants. Finally, some work has been done regarding physical interaction in this context. First, there is the work of Lee and collaborators in 2020, which enabled us to see that physical interaction were mainly happening in the upper part of the body. And finally, more recently, the work of Feldman and Adrian this year enabled us to understand how the perturbation propagate through a group of individuals. This new experimental paradigm was very interesting because they used a full body reconstruction of the body, and such paradigm could be used to study as well standing recovery. However, in this work, it was not used for this matter. Finally, we can look at what have been done regarding the standing balance of single individuals. As you may know, this standing balance has been mostly used to study the standing balance of single individuals. To do so, several biomechanical quantities have been proposed. Here we will focus on a limited number of those, mostly kinematics and kinematic quantities, due to the nature of our data, but also our aim to create a model that could be applied to large-scale simulation. I will come back on the relevant biomechanical quantities later on. We can have a look now at the experimental paradigms that have been used to understand standing balance following external perturbation in this case. So there is 2 main families of perturbation that we can apply to the body of participants. First, the non-compliant perturbation, And then the compliant perturbation. For non-compliant perturbation, the state of the body of the participant is fully defined by the perturbation itself. For compliant perturbation, the state following the perturbation of the body of the participant is defined by the perturbation, but also by the action that can take the participant while being perturbated. So for the first family, you have, for instance, an imposed center of mass, displacement, and velocity, or what is called, for instance, the tether release experiment, for which the body of the participant is placed in a critically unstable posture and then released. For compliant perturbation, there's, for instance, the moving ground experiments, which involve a moving platform beneath the feet of the participants, but also the force-controlled experiments, for which the participants are exposed to perturbation with a given force. Here we will focus on this last family of experiments, since they are the closest to what could be seen in dense crowds. Finally, we can look at the different recovery strategies that can be used following external perturbation. And here we will focus on first the non-stepping recovery strategies and the stepping recovery strategies. As you can see, there's different recovery strategies that can be used. Those depends on different factors. We can have a look to the different factors that can affect recovery strategy. So first, there is the intrinsic factors that are linked to the individuals, such as anxiety, which have been seen to create a greater body stiffness, but also the use of alcohol or drugs, for instance, that increase body sway, but also increase the reaction time. And finally, there is, for instance, age and age-related conditions, which have mainly be associated with more conservative recovery strategies. There's also factors that are coming from the environment, such as the type of terrain, for instance. For uneven ground, recovery strategy have been seen to be adapted, but also the angle of perturbation, which we have seen are associated with different types of recovery strategies. And finally, there is, for instance, the level of awareness to the upcoming perturbations, which have been seen to be associated with a larger displacement when participants had prior knowledge of the perturbations. Here we will focus mostly on those two last categories, since they are associated with conditions that could be seen during dense crowds. To wrap up what we have seen, so to be able to create a model for crowd simulation that would integrate a recovery strategy, we first need to be able to predict the step initiation, but also select the right recovery strategy, and then use, for instance, the correct stepping strategy. To create this model, we can use the tools that have been developed for single individuals, but we will need to investigate new experimental material regarding what happens for standing balance in crowded environments, since the current experimental data on this matter are missing. Regarding our contributions here, first, we propose a method to classify and separate the recovery strategy, enable us to predict recovery strategy. First, then we studied the characteristics of the steps associated with different recovery strategies. And finally, we had a look of how standing balance changed in different crowded environments. This work also enabled the creation of new experimental data sets involving novel experimental paradigms. Without further ado, we can step into our first experimental scale with the study of the standing balance of single individuals. Our objectives here were the following. So first, we wanted to predict recovery strategy based on individual kinematics. And then we also wanted to study two factors. First, the effect of the angle of perturbation, and then the effect of the level of awareness on the recovery strategies of the participants. Here is a view of the experimental design. So here we use a compliant perturbation as I previously said, and we mostly studied the motion of the participant here. This was done using a motion capture of the participants, but we also recorded the force applied to the participants using a force sensor. This experiment was undergone by 21 participants with so 21 young adults, sorry. And for each of them, the following experimental parameters were varied. So first, we tested 5 different perturbation angles with 2 sensory conditions. So one condition was not with no sensory impairment, and the second condition was with noise cancelling headset with plastic sheet mounted on the side. This would enable to lower the level of awareness to the external perturbation. And then we tested 3 levels of intensity to observe different recovery strategies. These parameters were repeated twice with a random order on the 21 participants. Hence, we end up with a bit more than 1,000 trials to analyze. To deal with our first objective here, we need to tackle 4 problematics. Here we will be only using the kinematics of the individuals. So we need first to estimate the perturbation angles, because we will have no prior knowledge of this for dense crowd experiments. We also need to label and predict the different recovery strategies based on this kinematics information, and not on the perturbation itself, since we will have no knowledge of this for crowd experiments. And finally, we want to investigate the characteristics of the steps. But to do so based only on the motion of the participants, we need to use quantities that would represent the different the motion of the participants. So here is the biomechanical quantities that we have used here. We computed them from the motion capture data, on which we fitted a biomechanical model. This allowed us to compute the position of the center of mass, which is the mean position of the mass distribution of the body. And we mainly look at the projection of the center of mass in the base of support. The base of support is the area between the area enclosing all the contact points between the body and the surface support. We approximated the base of support here with the external markers on the feet of the participants. Note that we have the base of support and the center of mass. When a perturbation was applied, the center of mass was moving in the direction of the base of support, and we were able to compute a distance between the base of support and the center of mass in this direction. Now that we have a distance and a velocity, we can compute the time to boundary. This time to boundary can be seen as the time required by the center of mass to reach the boundary of the base of support at its current velocity. We use this matrix as a measurement of the level of stability of the individuals. The minimal time to boundary obtained during a trial could be seen as a way to understand the minimal moment the moment where the standing balance was at the most critical state. We also investigate another quantity when steps were triggered. We looked at the boundary of the foot that stayed on the ground, the non-stepping foot, and we look at the distance between the center of mass at step initiation and the boundary of this foot which stayed on the ground. This was called the distance to foot boundary, and it will be used to separate the recovery strategies. All right, let's go back to our problematics. And first, we need to estimate the perturbation angles. So you might have wondered why have we not used the instructed perturbation angles? So we said we have tested 5 different angles, but here we are dealing with compliant perturbation. So we decided to take the ground truth angle as given by the direction of the center of mass at the maximum intensity of the perturbation. And we try to estimate this angle using the angle given by the direction of the center of mass at the moment of minimal time to boundary. Here is an overview of the results. So you can see that the ground truth angles are quite close from the instructed angles in black. And here is the estimated angles. So what you can see here is that the difference between the ground truth and the estimated angle is very close when a step was done during the trial. However, when no step were observed, the difference between the estimation and the ground truth was larger due to minimal time to boundary obtained during the recovery of the participants. So now we have a method to estimate the angle of perturbation, and we now need to label the recovery strategy and predict them. To do so, we developed a new method to label the different recovery strategies. This method involved the initial base of support, but also the trajectory of the center of mass in this initial base of support. For each possible trajectory of the center of mass, we associated a different recovery strategy, which could be used by the participants. Now that we have labeled our different recovery strategy, we could plot our trial against the perturbation angle and the distance to foot boundary. And what we observed is the creation with this plot of different regions associated with different recovery strategies. We then separate our regions using logistic regressions and create a model with different regions separated by the dashed lines here that will contain the different recovery strategies. So we would be able to predict recovery strategy based on the distance to foot boundary and the estimated angle. What we found was a good expectation rate, so the recovery strategy were in the correct regions of the model with more than 88% of the trials. The accuracy of the separations also excellent results with an accuracy above 72%. We repeat similar methods between the trials with steps and without steps. And we observed here again an excellent separation between the recovery strategy. This separation was here done with the minimal time to boundary observed during a trial. We can now see how we tackle our last problematic, the step characteristics. And to do so, we see how we tackle our last problematic to compute the characteristics of the steps based on kinetic information. We use the transversal velocity peaks given by the steps, and we look at the inflection point before and after the transversal velocity peaks. That gives us the beginning and the end moment of the steps, and hence we were able to compute the step length, but also the step durations. With this length and duration, we could compute the average speed of the step. And finally, we also looked at the deviation of the step, which is the angle between the step vector and the estimated perturbation angle. Here is our results. So here I will be only showing the result for the forward recovery strategy because the relationships are the clearer here. However, different observations have been done for all the recovery strategies. What we observed here is a relationship between the momentum associated with the center of mass, which is linked to the perturbation intensity, and the step length and step average speed. These have been also seen in the literature, as well as constant step duration, which can be seen with a good relationship between the speed and the length of the steps. However, in our experiment here, we observed shorter steps compared to the literature. Finally, looking at the step deviation, what we have seen here is that in this context, the step deviation was converging with the momentum associated with the center of mass. We can now conclude on our objectives. So first, here we were able to create a separation model, allowing us to predict recovery strategy based only on kinematic information of the participant. To do so, we created a new method to label the different recovery strategies. We also found that we could use the time to boundary to predict the limit before step initiation. And finally, we found interesting characteristics of the steps that are related to the momentum associated with the center of mass. And we also observed that the deviation of the step was reduced with this momentum associated with the perturbation intensity. Finally, regarding the different factors that we have tested here, we observed a strong effect of the angle of perturbation with different stepping strategy associated with different step characteristics, but also different limits before step initiation. However, we did not observe an effect of the level of awareness as we tested in this experiment. Regarding the limitation and perspective of the study, here we used a new method to label the different recovery strategy. However, this method comes with hypotheses that have to be acknowledged before being used. And we think that this method could be improved using other metrics, such as the center of pressure. It would be also very interesting to test different experimental factors, such as age or uneven ground, since those could be seen in dense crowds. Now that we have seen how to separate recovery strategies, we want to know if the method that we have developed here can be applied to dense crowds or to events involving multiple individuals. To do so, we can move on to our next experimental scale with multiple individuals. Here I will present results which I've obtained using a data set that have been created by the Empiricism division from the research center of Jülich in Germany. I had the chance to take part in these experiments in the frame of the European project I was working on, ProDNA. And I will present now the results that I've seen during this experiment. Our objective here are first to compare the recovery strategy of single individuals and the one observed during an experiment involving multiple individuals. And in the second time, we want to understand the effect of crowding on recovery strategies. So here is an overview of the experiment themselves. These experiments involved 20 young adults, so the same population as we studied before. And during this experiment, we mostly investigated here the full body motion of the participants. However, video recording of the experiment has been done, as well as recording of the perturbation intensity using pressure pad attached to the perturbation device. Regarding the experimental parameters varied here, the results will be showing are only through the investigation of 4 group configurations here. However, 27 group configurations have been tested during this experiment. Here you can see that the orange circles represent the participants with motion capture suits, and green participants represent extra participants that were placed on the boundary to ensure the same behavior for all the orange participants. We also test 2 interpersonal distancing conditions, with the no distance, with participants being in contact with each other at the beginning of the experiment, and the elbow distance condition, with participants being at 1 elbow distance from each other. These parameters were repeated 3 times on the 20 participants, and we obtained a bit less than 500 recordings. However, here we only investigate a fraction of these recordings, since not all the participants were affected by physical interactions. Regarding the variables that we have used here, they are the same as the one presented before. However, we will be also looking at environmental characteristics with the interpersonal distance and the density. Regarding the density, first we looked at the distance to the upfront neighbor, and what we can see is 2 different groups associated with the different distancing conditions. There's a mean distance of 16 centimeters between the 2 experimental conditions, and this led to 2 clear regions of density. However, you can see that there's an overlap between the density regions, but this is due to a different method to compute density for the group involving only a line of participants. If we remove these data points, we can clearly see that there is density around 4 for the elbow distance condition and a density above 6 for the no distance condition. Regarding the effect of this density, first we will have a look to the angle of perturbation. So what we can see is that for trial in which a step was used, before we have observed that this was the closer to the ground truth perturbation, and here it's in agreement with the experimental protocol. However, where no steps were taken, here it's still difficult to conclude because it seems that some perturbations are wrongly estimated. Regarding the effect now of the density, what we can see is that step initiation was more conservative at elbow distance, meaning that people will tend to step for less critical situation. But also we observe a leaning behavior at no distance. So it's a recovery strategy, leaning on the participant up front, and then recovering without taking step. This could be seen with critically unstable time to boundary, but no steps of the participants. Regarding the step characteristics in this experiment, we can see that shorter steps were taken compared to to the regression. So this regression corresponds to the regression for single individuals. So we can see that data points are below the line observed for forward steps of single individuals. So we can see that there's shorter steps used by participants during the with multiple agents, but also slower steps with data point being below the regression obtained for single individuals. However, regarding the step duration, we observe a close relationship with what have been observed before. And last, regarding the step deviation, here, first for single individuals, we observe a convergence. However, here, the step deviation was not converging with the momentum associated with the perturbation. Regarding our objectives here, first, we found that the limit of before step initiation was comparable to what we have observed during the single individuals. However, we observed also leaning behavior, even though we observed only a very limited number of those. Regarding step characteristics, we observed shorter but also slower steps than during the single individuals, with a constant step duration, so the same as the one used by single individuals. And finally, the step deviation here was not converging with the momentum associated with the central mass. Finally, regarding the effect of crowding on recovery strategy, we observed a more conservative limit before step initiation at elbow distance. And we also observed that the leaning behavior was only observed for the non-distance condition. So when participants were already in contact with each other. We did not observe an effect of the crowding on the stepping recovery strategies, on the characteristics of the steps. Sorry. To push further the result we had during this experiment, we can think of investigating the physical interaction themselves during these experiments. In the manuscript, we proposed a study of the hand raising of the participants. However, this does not correspond to the physical interaction with participants, since contact could happen before. So to do so, we could use pressure pads, for instance, but this add up more complexity to the experiment, and will require the use of multiple pressure pads. So it add a real challenge to the experiment. We could also push further our analysis on step characteristics by looking at the relative foot placement. This could be done with the merging of all the motion capture, but also we could look at the perturbation propagation. But this work is currently being done by Sina Feldman, whom I had the chance to collaborate with during my PhD. Now that we have observed how standing recovery changed with multiple individuals, we want to see how the behavior we have observed are still visible for a real dense crowd event. To do so, we moved on to the last experimental scale with an experiment taking place during a punk rock concert. The objective here are first to study the application of the method developed before, but also to understand, to compare the laboratory experiment with data acquired in the wild. The experiment here happened during the Hellfest Festival, which is held every year in Clisson, in France. And our experiments were performed in front of one of the 6 stages of the festival. This stage is called the War Zone, and it's dedicated to punk rock music. This type of music is associated with a special type of dancing, which is called moshing. And moshing happens in an area in front of the stage called a pit. In the pit, physical interactions are socially accepted, and we took advantage of this special condition to perform our experiment. The experiment were done on a flat surface, flat paved surface, so comparable to the one we tested during the experiment, during daytime. Sorry. The apparatus was the following. We recorded the motion of the crowd with RGB videos, but also the motion of the participant with Nixon's suit, so the same as the one that were used during the multiple individuals experiments. Here are recordings of the pilot experiment we performed last year. This year, we added an experimental protocol which enabled us to study standing balance in this very context. The protocol was self-initiated by the participants, and they had to clap to indicate that they were standing in a stable position. Then they would wait for external perturbation, and the trial would be ended at the end of their recovery strategy. They can also double clap to indicate that they will take voluntary steps. The protocol was performed by 3 participants during 2 concerts. Here is a glance of the results. So what we can see here first is that perturbations were happening from all possible directions in this context. We can observe here a new recovery strategies involving backward steps, which have been not seen before. Regarding our separation model for recovery strategy, we found that the model that we developed using data of single individuals was performing well to separate the recovery strategy. However, for the region associated with loaded side steps, so those were struggling to find the correct recovery strategies, with expectation rate being quite low. However, we were also able to create a new region for our model containing the backward steps with a good accuracy of the separation. Finally, we looked at the step initiation, and what we observed is that most of the recovery steps that we have seen were below the limit after which step initiation was done during our laboratory experiments. So we had a good agreement with the laboratory experiment here and the field experiments. And finally, we looked at the characteristics of the steps. So here only the forward and backward steps. And we have observed that first, the recovery steps were shorter compared to the one taken by single individuals. So they used shorter first recovery steps, but the step duration was also faster to what was observed during the group experiments. So they were taking shorter and faster steps in these conditions. Regarding the step deviation here, we observed the same phenomenon as we observed during the experiment in laboratory involving multiple individuals, with no convergence of the step deviation. Finally, regarding our objectives, the separation model that we have created earlier was showing a good estimation of the recovery strategy used here, except for one of the recovery strategy. We were also able to create a new region for the model involving backward steps. Regarding the difference between the recovery strategy observed in laboratory and during the field experiments, first, the perturbations here were coming from all the possible directions, but the limit before step initiation was here conserved. And finally, steps were shorter. The first recovery steps here was shorter, but also shorter than single individuals, but also faster than what was observed in dense group condition in laboratory. what we can say in view of these results is that first it's a proof of concept. Here we only took the data from 3 participants, but then our protocol may also induce involuntary factors. Being passive in a pit may have increased anxiety of our participant to physical interaction, which could have led to body stiffness and could explain part of the result, especially for the different step characteristics. Finally, here we investigate a very particular social context. However, the protocol that we have used here can be used in other contexts involving dense crowds. So now we can conclude about the general work proposed here. We have used a multiscale approach in this work, and this enabled us first the creation of a model that could be applied for recovery strategy in dense crowd simulation. This model does not rely on information regarding the interaction, but on the induced body motion. And with this body motion, we were able to predict recovery strategy and, to a given extent, prevent the recovery steps. Predict the recovery steps. Finally, we also investigated different experimental factors changing the recovery strategies. First, the angle of perturbation, which shown to have a great effect on the recovery strategies, with different recovery strategies used, but also a different limit before step initiation and different step characteristics. Then the level of awareness, which have been shown to have no effect, at least in the context that we changed it here. And finally, the presence of other individuals here have been observed to change the limit before step initiation, but also the characteristics of the steps. Regarding our methods here, we decided to use an approach based only on kinematic information. However, our finding could be deepened using other metrics, such as the center of pressure or pressure pads to study physical interactions. Also, here we only investigate the first recovery steps. However, recovery strategy in this context could involve follow-up steps. But to do so, we need first to be able to separate voluntary and non-voluntary steps in this context of dense crowd. This was a real challenge that we faced during this work. And finally, here we only investigate standing balance. However, balance have also to be regained during locomotion tasks, for instance. And this should be investigated in the future. Finally, regarding the perspective we now want to see. So first, we want to see this model applied to crowd simulations. So this work have already been studied by Jensen, which I had the chance to collaborate with during my PhD also. But it could also be applied to different crowd simulation. Then different experimental factors can be tested, such as age or change in perception, using, for instance, mixed reality. And finally, it would be very interesting to understand the origin of physical interaction in dense crowd, how they are initiated and why they are happening. And to do so, we could use the final experimental protocol that we have proposed here in different contexts. Thank you for listening, and I will be now glad to answer to all of your questions.
Thank you, Thomas. Merci pour cette présentation. On va immédiatement, en effet, passer aux questions. We'll immediately begin with the questions, and we'll begin with the first reviewer of your manuscript, le premier rapporteur de ce travail, Thomas Robert, que je laisse prendre la parole.
So thank you, Thomas, for this very nice and very clear presentation of your work, and thanks for your advisors and directors for the kind invitation to review this work. So maybe as you have seen from the lot of comments I put in my report, so your work, I found it really interesting. So you should take it as a proof of interest, not criticism. So I found it really interesting because, well, first it's the topic itself is challenging, and what I like is that you kind of face this challenge to go to we can say wild conditions. So and you did it actually. So at the end of your work, we have an experiment in a really ecological. We can discuss it, but in a kind of crazy situation, and you get some relevant data out of it. So I really appreciate that. I also really appreciate the fact that I had a lot of fun just looking at the picture of the experiment. First, because they are fun. Okay, first thing that you see when you open your PhD is someone trying to push someone else with a broomstick. It's like, what the hell are they doing? And then you have a picture of people with strange orange hat, and then a punk rock concert. So it's a bit disappointing at first. But to be more serious, what I really like with it is that it really shows a very nice, progression in your work. So it starts with it's very logical, and it's really well highlighted by these three pictures. And last thing I really wanted to, well, not the last, acknowledge is the amount of experimental work and data processing that you've done. So there's a lot of things in your manuscript. And I also enjoy the fact that you cropped some of it in your presentation, because maybe it was a bit too much. So I really also like the fact that in your presentation you took into account some of my comments, and I found it much more clearer and a bit easier to get the salient result. Okay, that was a positive part. No, I'm kidding. Obviously, well, it's a job to ask questions first because I have questions, and also it's part of the game. Where to start? So maybe we can start with balance recovery strategy that you describe. You very quickly mentioned the fact that you also have some that you focused only on linear momentum kind of strategies, so looking at displacement and velocity of center of mass, and kind of get rid of the angular momentum. I think Bruno will come back on this later. So if we go back to something that you did not really describe in the presentation, but it was in the manuscript, it's this leg abduction strategy.
Yeah.
And you describe it as a change in support kind of strategy. And keeping in mind that maybe also if you get rid of this, if you go a bit further than just a linear momentum balance recovery strategy, don't you think that maybe this leg abduction, instead of a change of support, because it doesn't bring much as a change of support, maybe it's more like a regulation of the angular momentum?
Yes.
I just wanted your point on it.
Yes, definitely. Although it was, so in my manuscript, I placed this strategy, so in between actually the change in support and the non-stepping recovery strategy, because it involved, so for those who don't know, it involved just lifting one leg to regulate the angular momentum and then replace it where in its original position. And yeah, this strategy is very challenging even to label, because it's difficult to, I mean, you can also do this and then replace your foot somewhere else, right? So it adds another complexity on how to label recovery strategy. that was actually a real challenge to be able to label all the different recovery strategies. Yeah, I do think that by looking at, for instance, the angular momentum, we can have observed a signature associated with this recovery strategy.
I think so also. So still in this recovery strategy, there's something that you indeed mentioned at the very end. The limitation is that you focused on one step.
Yes.
Which for your first experiment looks really relevant, because I don't think that many people did multiple steps. I don't know exactly. And my comment is in this, I don't know exactly. So it would have been like super interesting if you could provide. I understand the difficulty for in some context, but I think if you do not provide more information on this, it's kind of a limitation, because knowing that you have short step, if it's one step among 6, well, okay, that's an information, but what to do with it? And if you look, I think among the one figure in your manuscript that shows that could provide some kind of information, it looks that you have many recovery steps, many small recovery steps, and I suspect that it happens as the situation gets more complex.
Yeah, exactly. It's a very interesting point. Where to begin? So yeah, let's take it from the scales. So first at individual scales, for instance. So you said there's maybe just one step, but actually sometimes, so people were asked to react as they would have done in real conditions. So it's always difficult to, they are like in the gymnasium being recorded. So it's so we asked them to act as naturally as possible. But some of them just really take a step, but others were taking a step and then taking another one to go back to their place, right? And some of them took, 2 steps and stopped here, but some other took the same 2 steps and then took a third one, right? And so if we are not able to discriminate voluntary and non-voluntary steps, then what do you do with the last one? And this was, so we actually think of involving all the recovery steps. However, it was difficult, like sometimes we had to crop the final one, but sometimes the final one was one of the steps taken not voluntarily, but to recover from the perturbation. And this was increased with the scale, right? So when you had different individuals in the same setup, then you have the motion of other individuals that will affect the motion of your individual you are looking at. So there's like social constraints, like your neighbors is moving your way, you just have to, not collide. So this add up complexity. So actually in the figure you mentioned, there's several steps, but so I double checked it, and I think there's like 2 steps in the end that are just moving backwards because their neighbor were going in their direction, And when it gets to field experiment, then it's a real mess, if I can use this word. Like you are using a very complex recovery strategy, and what we can say is that only the first recovery steps are taken because of the external perturbation. Or it was our approach, like. If you wouldn't have stepped to recover balance in this context, then you would have fallen. Or you would have like...
I think the only thing that you can say is that people took step. You don't really know exactly what would happen.
The first one is, the one that like you could... I mean, to our point of view, it's the first one that you can compare. Like it's the only one that you can compare between the scales.
I agree that, the fact that you trigger a step is an information, and you don't care if you trigger 1, 2, or 3. The fact that you have to trigger 1 is it's important in itself. But how to interpret the fact that a step is longer or shorter if you don't have the same level of perturbation, if you don't have the same instructions, if you have many steps behind. That was more like the open question. I understand the constraints, strong experimental constraints that you had. But given that, would you keep the same instruction for the subject? If you had to do it now, would you go for like stricter constraint, or weaker, or the same?
Yeah. So you think about a single individual?
For the first experiment.
Yeah. So I would say it depends on what you want to look at afterwards. So if I would. I can only say it depends. I mean, it depends on what you want to observe.
Typically, if you want to focus on step characteristics, I guess it's a way to prevent as much as possible the fact that people do unnecessary step, or what you call voluntary steps. So you say you ask them to do as few steps as possible, like one, and if it's more than one, it's over. For example.
Yeah.
So,
but what I would probably do is use like if I had to do it in a laboratory, then there is maybe ways that could be used to analyze if steps are voluntary or not. Like you can base your result not only on the kinematics, which have been done here, but on other information. You can use EMG or like other informations. And that's probably what I would do, like use other informations and not only focus on kinematics. Here we only focused on the kinematics since we knew that that would be the only information we will get in the end.
Bruno, tu m'arrêtes, hein. Moi j'ai des questions pour la soirée. So okay, I have some other questions related to the fact that what you try to describe, well, not only, but is a limit state which trigger a perturbation. So which raise also some questions like why choosing to try to find a limit, a state of a person instead of a perturbation to trigger, because and this goes back to a question that I think we both raised in our report is what would you do with the data? How do you want to use this data? I mean, because if you go to the literature about balance, many people look at what is the limit perturbation, because this is what you can apply to someone before he has to do something. But in your case, you just look at the state of the person. And okay, well, the state of a person just before a step will tell you, obviously, if you will step or not. But if you try to look at this state like a few milliseconds later, you will actually see the step. I don't know if I'm clear. So you can describe these boundaries, these stepping boundaries, in terms of state or perturbation. Like.
Exactly. So we wanted to use the state of the participant due to the simulation paradigms that are currently used. So basically, we want to use this approach for what is called microscale, but it's like agent simulation. So so each agent is like an entity with information that are intrinsic. And what can happen is that there is several perturbations. And if you take a perturbation that will trigger a step in a given direction, maybe you will receive the same perturbation in the opposite direction. This doesn't mean that you will trigger two steps, but maybe they will annihilate and you will stay in the same position. So this is why we choose the approach of looking at intrinsic information, so the induced motion and not the perturbation themselves. But I do agree there's a lot of literature regarding perturbation, and it would be also nice to have like a gap and be able to use those information to like feed models.
No, but I mean, I'm convinced that it is a good choice, and your answer is really clear. My comment is more that we couldn't see it as clearly, I think, in your manuscript or presentation, maybe even in the presentation. So, and it's a bit sad because I was quite sure that it was really clear in your mind, but okay, I'm happy to hear it. Did you observe any fall? Une autre. Okay. So I have so many. So did you observe any fall?
So yeah, during the multiple individual experiments. So not in the presented results.
Okay.
But we do have a motion capture recording of people falling during this experiment. So the experiment was performed by. So the main investigator was Sina Feldman and Julien Pettré. And what they observed is so they had this experimental condition where people were trying to push in the center. So there was like one person in the center being pushed by 30 participants, being pressed in the middle. And in fact, the density couldn't get higher. And then when they said stop, people had to release, but then the constraints were not released at the same time. And so some people were still, trying to not fall, so pushing on the other ones. And what we observed is like the beginning of a shake in the groups, and then at some point the pressure was released too strongly in some part of the group and not at the opposite, and this created falls. Yeah.
No, it was more related. I find it really interesting, but so should we really say that what you observe is a limit state, as you do not have fall, or it's like chosen boundary by the subject?
Yeah.
That's more okay, but we can debate about that. I have many questions about the metrics that you use, but we can discuss about it later. Maybe the last question is. You said that you have, and you actually have really nice data sets. Will you provide them openly, publicly? Yes. When? How?
It's been also a question that I've been asked in the last conference we did in November. They will be released. So the data set from Julich, it will be released in beginning of next year. They have been working a lot on it, and it's almost ready. My dataset is ready to be also put online. The experiment about the last experimental dataset that we have created have to be checked because it involved. So maybe the motion capture could be sent online, but not the video recording so far. Work have to be done on them, but definitely they will be available.
Okay. Thank you.
Thank you very much, Thomas, for this discussion. Now we will give the talk to the other reviewer, Bruno Watier. It's me. Thank you very much. And I fully agree with Thomas about your very, very clear presentation, which on top of that highlight some unclear points of the manuscript. Those I fully enjoy your presentation. Thank you again about that. Of course, now I will ask some question, and perhaps to be clearer myself, I will ask the question in French, but you can answer in French or in English, of course.
I might answer in English, so.
As you want. Ok. Alors, je vais être un peu provocateur pour la première, et je vais aller du plus haut au plus bas. Finalement, vous avez montré dans votre travail que plus on pousse fort et plus on fait des grands pas, pour se rétablir. Et que finalement, quand on vous pousse dans une direction, la vitesse du centre de masse va à peu près dans cette direction. Mais finalement, je suis resté un petit peu sur ma faim, sur finalement une foule, qu'est-ce que ça risque de générer. Bon, oui, je vous pousse, vous faites un grand pas si je vous pousse fort, un petit peu. Mais qu'est-ce que vous en retirez sur le comportement des foules?
So it's an excellent question.
I hope an excellent answer.
No. So there's for instance, what we have observed is so the convergence, for instance, of the step deviation. This was very clear for single individuals. However, for multiple individuals, this behavior was so it still happened because at lower for low. Oops, I lost. I could use a slide for that. If you allow me, I will just come back here. Okay, so this is what we observed here. So, for instance, there's a clear convergence for single individuals, but it's definitely less clear for group and in crowds. However, so here is it's a zoomed-in picture, but what you can still see is a convergence. So you see that you are stepping, so as you said, in the direction of the central mass. But so there's still so the stronger the perturbation will be, and what you can see is that the stronger it will follow the direction of the perturbation, and this will happen in crowds. Right? However, if the perturbation gets diffused, participants will be able to step on the sides and then diffuse even more the perturbation itself. This is very interesting for crowd dynamics because it would mean that you will have a recovery capability of participants to steps in between or steps in the direction out of the perturbation, and then reduce the propagation of this perturbation. Right. Regarding the step characteristics, so what we can what we can say about the characteristics, for example, the one we observed in dense groups, is that they were slower than the one we observed in this context of concert, and this could indicate participants were also using their environment to make sure that they were not stepping on anyone. This was maybe, so it needs to be validated since we only had 3 participants here. This was maybe not the case for these participants since they were taking faster steps, right? And so you can see that the social context in which the participants were would influence the stepping recovery strategies. And if you have so if you are forced to make faster steps, this is even more challenging for your recovery strategy. So all this information is knowledge that we can apply to understand collective motion in crowds. I hope this is okay.
Thank you for the exhaustive answer first. Oui, parce qu'une partie au départ de l'introduction porte sur les risques vraiment générés par ces mouvements de foule qui, vous l'avez noté, peuvent être dangereux. Et dans les témoignages que vous avez reportés dans votre manuscrit, les gens disent, voilà, en fait, j'étais dans une foule et je me suis retrouvé devant un mur de gens qui étaient déjà tombés et ils ont trébuché. Effectivement, quand on lit la littérature sur les chutes, en général, soit on chute parce qu'il y a un obstacle et on trébuche vers l'avant, soit on glisse et on tombe vers l'arrière. Alors vous avez choisi de pousser en haut, mais il n'y avait pas d'obstacle devant. Parce qu'on peut comprendre aussi que on est poussé à la fois par derrière et en même temps il y a un obstacle devant, donc ça devient dangereux. Vous, non, vous êtes arrêté à la moitié, vous avez poussé derrière, mais comme il n'y avait pas d'obstacle devant, et d'ailleurs on le voit un petit peu finalement, parce que dans les expérimentations que vous avez faites, ils arrivent à faire un pas en avant, ils ont la place, donc la dangerosité, vous avez réussi à en faire tomber quand même, bravo, mais et bravo aussi pour le CPP, hein, félicite, vous avez dû y passer un peu de temps, mais bravo. Oui, voilà. Je me demandais si les conditions aux limites de vos expérimentations étaient représentatives des risques réels de ces foules. Je ne souhaite pas, à la limite, je ne sais pas s'il faut reproduire des risques importants. Ça peut se poser d'un point de vue éthique, déjà, c'est vrai. Mais je pense que je me demandais si ça répond vraiment aux risques encourus par des foules de chutes graves, ce protocole.
C'est une question qu'on peut se poser. Mais oui, il y a plusieurs réponses à cette question. Et oui, une réponse évidente est clairement l'éthique que ça pose. Sorry, I will continue in English. So the question was about how representative the experiment we performed were compared to real dense crowd disaster that have been observed, for which stability was not only perturbed by the perturbation themselves, but also with, for instance, difficult ground conditions and multifactorial multifactorial falls. So this is why also we wanted to investigate different factors which influence the standing recovery strategies. We tested here only two factors, and we really hope we could see like an effect of the level of awareness, because it has been seen, as I've underlined it in my manuscript, that participants seems to have felt, because they couldn't predict, that they were placed in a challenging situation. So we wanted to see if we could replicate such an effect using our sensory limitation device. However, since we did not manage to find any effect, this approach was then a bit compromised. What was compromised is, how can we place people in a safe manner, controlled manner, with such different factors. And this is still very challenging. Experimentally speaking, how do you create an environment that is close enough to what you can observe in crowds, dense crowds? So this is why, we choose to investigate external perturbation only. External force-controlled perturbation, because external perturbation, as you underlined, could have been something on the floor. Actually, this is an experimental paradigm that is investigate to study standing balance of a different population. If you would have done this in a context with multiple individuals, first you would have led to very challenging experimental issues that we would need to solve. Here the experiments were performed in a hall which was not equipped at all before the experiments. It was in a university, so we needed a large area that could contain more than 100 participants, because here there was only 20 participants, but the experiment involved at least at least 30 experimenters and like hundreds of participants. So we needed space, all these infrastructures. So yeah, it's very challenging to set an environment that would be similar to what can be observed in the school. And this is the reason we proposed the LAAS protocol, because with this LAAS protocol, we could go in the field and be free of this limitation that are due to laboratory experiments.
Okay, thank you. And je vois que vous êtes un peu bavard, je vais vous poser une question qui, du coup, vous risquez de prendre beaucoup de temps pour y répondre, mais comme vous avez utilisé le terme plusieurs fois, là, vous êtes à l'équilibre, mais êtes-vous stable?
Oh yeah. Yeah.
Bon courage.
I may have used stability is a tricky word to use, and I made the mistake of using it. But yeah, I don't really like because it's hard to define. I mean, there's those those words that are commonly used and are hard to define, like crowds, for instance.
Yeah. And be careful with the words.
Yeah.
Each word has a sense, and
in
a mechanical point of view, stability is very well defined.
Yeah.
Equilibrium also. Balance a little bit less, perhaps, but indeed, it is an open door, and vous pouvez dire beaucoup de choses approximatives. Oh, sorry, il faut que je parle dans le micro. Voilà. Et effectivement, du coup, vous avez choisi d'étudier. Je préfère finalement dire l'instabilité, parce que j'ai l'impression qu'on est toujours un peu instable. Hein. C'est une position où le centre de masse est au dessus d'une surface d'appui, on est toujours instable. J'ai l'impression qu'on est parfois beaucoup trop, voilà, ce qui amène à des chutes, mais l'instabilité, si je vous pousse un peu, on vous verra bien que vous êtes instable, hein, très probablement. Vous avez choisi en effet d'étudier la position du centre de masse par rapport à la surface d'appui. Oui, vous en avez parlé. Il y a d'autres critères. Je ne vais pas revenir parce que ça serait pléthorique, hein, le nombre de critères possibles. Et en effet, le moment cinétique me paraît être aussi un paramètre. Bon, Thomas en a déjà parlé, donc comme il m'a volé ma question, je ne vais pas en reparler. Bon, tu l'as à moitié pris. Bon, une question sur la méthodologie, puis après je m'arrête, parce que même président, j'ai pas le droit à plus de paroles que les autres. Donc vous avez en effet étudié ces critères cinématiques à l'aide de la mocap dans l'étude 1, l'analyse de mouvement tridimensionnel avec des caméras, qui est ce qu'on appelle le gold standard en analyse du mouvement, hein, parce que c'est précis. Bon, quand bien même ensuite les procédures de cinématique inverse génèrent quelques artefacts, il n'empêche que c'est ce qu'on sert comme le gold standard. Alors après, vous avez utilisé des X-Sense, donc qui sont des matériels avec des centrales inertielles dont on sait au contraire l'imprécision liée au drift, liée à plein de choses que vous connaissez sûrement tout aussi bien que moi. Et il m'a manqué dans cette étude, dans ce manuscrit, le lien entre les deux, c'est-à-dire la précision qu'on a de l'un par rapport à l'autre, et ça aurait été bien de voir, de comparer les données obtenues par l'analyse du mouvement et par les données X-Sense. Alors l'avez-vous fait, et pensez-vous que voilà, soient comparables les études 1, puis 2 et 3 au regard du protocole expérimental?
Alors, je crois qu'il y a plusieurs questions en ligne, je vais essayer de les prendre une par une. Donc, par rapport à related to the computation of the biomechanical quantities. So first, regarding the base of support, we so for the first experiment involving X-Sense, so the one done during the experiment in Wuppertal, performed by the group in Jülich. For those, there's actually research, as you mentioned, that exists, that have been done to validate, for instance, the relation with the base of support. And what have been observed is that the error with comparative motion of the participant, the typical error that could be seen was like 1 order of magnitude below the effective displacement of the central mass. So we acknowledge this information, and we decided to still work, knowing that our result would have like an order of magnitude, like the difference would be 1.5 centimeters, and here we have like more than 15 centimeters of displacement, for instance. We did a pilot experiment for our first experiment, in which we used both. However, while we computed our biomechanical quantities, we could not find a significant error between the two. So we decided to stick with the optical system this time, because we knew that it was better. Since it was a pilot experiment involving 2 participants, we did not push the investigation. But where it's very important would be for the last experiment, since you said, yes, there is drifting, and there's just drifting with motion. And in this last experiment, we had participants walking through the stage and then being here. However, in this context, it's impossible to test with a different system. So yeah, we were limited in this situation. So yeah, we acknowledge this. So results here have to be considered as they are, and knowing that we could not validate in this very context.
Yeah, I agree with you. XSense is probably the best to obtain these different kinematics of the segments. Okay. Thank you for your answers, and now I will let the examinator for the discussion, and we will begin with Cécile Apper-Rolland from Orsay.
Thank you very much. Can you hear me?
Yes, very well.
Okay, thank you for the invitation in this jury. I appreciated it all the more that I find it's very interesting what's going on in this field, because for a long time we have written in the introduction of our papers that our research was justified because dense crowds were dangerous and so on. But actually we were looking only to low density pedestrian dynamics. And in these last years, we have really seen the emergence of several approaches to at last tackle really dense crowds. So it's difficult. It's difficult in particular because of these security issues. But I find it's really worth trying to go in this direction, and this thesis participates to this effort. I really find it very interesting. So your first achievement was to choose a good subject for your thesis, I would say. Okay, it's a game, so I will ask some questions. I have several of them. So one first was, okay, you have related somehow the kinetic information prior to the step to the different strategies. And then we want to relate from the perturbation to these early kinematics. If I understand, even in your first experiment, you don't have directly the information about the direction of the perturbation, because you take the maximum of the, well, you take the direction of the center of mass when you are at the maximum speed, if I understand. That's the ground truth. So you call it ground truth, and I was wondering, is it really ground truth? I mean, it's already an approximation, and you could have markers on the stick. Would it be enough? Could we have a better estimate of the perturbation?
Okay. So thank you. I'm glad that you asked this question. I can actually, come back to the relevant slide. So indeed, here, what you can see is that we add actually markers on the perturbation device. And but the tricky question is, what is the direction of perturbation? So the direction, since we are dealing with a compliant perturbation, the direction of the perturbation changed along the perturbation. So we could have developed several methods to quantify the direction of the perturbation. Since we have an infinite number of angles that the stick took along the perturbation. So here we decided to quantify the perturbation based on intrinsic information, but we could have also looked at the direction of the stick, for instance, at the moment of maximal intensity of the perturbation, which is close to the direction of the center of mass in this moment. But we could have also average, if you want, the direction of the perturbation device along the perturbation. We could have average and use a weight which correspond to the intensity, for instance. So the maximal intensity, the angle at maximal intensity would have the maximal weight. So there is different method that we could have used to quantify this angle of perturbation. So they are all there are pros and cons. And here we decided to use so the quantity I've shown you. So it's the direction of the center of mass at here. The direction of the center of mass at the moment of the maximal intensity. So this is why we call it ground truth, because this information could have not be investigated if we did not have information about the intensity itself, the intensity of the perturbation. You can't see if I'm showing here, you can see what I'm showing. But I hope it's clear that I mean this quantity we chose it among a number of representation that we could have used to designate the perturbation direction.
Okay, so it illustrates that it's complicated already to define what is the perturbation direction. Good. The second one is for the concert. You say that you compare the separation model with what you had done previously on the control experiment. But if I understand what you compare is that you take the same model, the same approach, but still you have to determine the boundaries anew for this new experiment.
So no, actually here on the model, so the model is the same. The boundaries are the boundaries that we found with the single individual experiment. There is only two boundaries that have been added. It's the boundary that correspond to to the region that is the CBS, so the central region for backward steps. And
okay, so because you had a table saying that you are doing again logistic regressions, but that's only for the new boundaries.
Yes.
Okay, great. So that's quite remarkable that still you have 80% of, more or less, of a good prediction. Okay. In your conclusion, you are saying that, let me take it. It's almost the last sentence, that using, that you could couple the proposed models with computer vision systems and detect step triggering to assess the level of balance of people in a given crowd. So of course, this would be interesting if we could do that. But I don't really see how you would detect steps triggering from these computer vision systems, or what do you call, because if you just have videos from the top, it may be difficult to assess step triggering from that, right?
So the idea, so it's a perspective, but the idea was to, if you could, so there's method to associate it, to track the heads, right? And with so now with OpenPose, there's methods to associate it to a video given motion, body motion. So you could have then an estimation of the body posture, and by using a biomechanical model using the posture you would have determined with this neural network, you could have access to the same biomechanical quantities. And then by having these quantities, you could estimate the velocity. You could also imagine approximation. So with the velocity of the upper body that you see, because in very dense crowd, you can only see the heads or the head and shoulder. So what you can think of is maybe approximate the actual momentum with the velocity of the visible part, and by doing approximations such as the position of the base of support, so you can expect the base of support. So this would require other experimental investigation, but well, I do think it's feasible. And so with the information you could get from the video camera, you could have an estimation of, or you could propose a model to estimate step triggering in this context. However, it's just an idea, and I have no idea of how accurate this method could be. But I do think, yes, that we can propose an approximation to that.
Okay, thanks. Going back to more details, I would say. So one important thing to determine your observables is this definition of the base of support. And you show that using the markers that you have, so you will take a polygonal shape that doesn't completely match the feet. Couldn't you just use your drawing of feet to have the toes and have a better shape, to have a better estimate of your base of support? Even if it, of course, you will not measure the real feet of people, but just having this drawing.
Yeah, yeah. I don't think it would be. It would just. I think it would replace an approximation by another without knowing if this approximation is better or not. To me, for me, the only way to improve this measurement of the base of support is by actually measuring it. So with pressure soles or force plates. However, it has been shown that that the center of mass before step initiation do not reach the base of support. So it never, and that has been also observed in the experimental results that I've obtained from my work. The step would be initiated before reaching the base of support. There's like a very limited number of cases where the center of mass exceeds this base of support. But by using those anatomical landmarks, it allows at least to have replicatable methods. So we know we use here landmarks that are possible to use on every humans. And if you use a model of fits, then there's like so many fits that could be. I mean, it's like an infinite possibility for fits.
You think it's not so critical because stepping anyhow doesn't happen exactly at the border. So okay. I had a question about when you work on real data, there is usually a lot of hidden work going from raw data to trajectories of markers, assessing markers to linking markers to a given person and so on. So I understood that for the second experiment, the group 1, this was done in Jülich. But how much of this did you have to do on the first and last experiments?
How much did I process myself?
Yeah.
So for the first and last experiments, I think I did it all. Yeah.
Okay, that was underlying it. And maybe my last question, which is more a remark, is okay, you are looking for dense crowds with physical contacts, and you say it's not so many of them. Well, when you live near Paris, you know that there is a good opportunity when there are strikes. You go in the subway and you have a lot of them. Did you ever think, I don't know if you can put in a project that you expect to have strikes, but at least you are ready. Did you think of using this kind of situations?
Yes. So actually, I thought of using different crowded environments. My initial thinking was one of the events that is also being investigated by another European project. So you may have heard of it. It's the light show that is happening every 8th of December in Lyon. Well, I guess Thomas can relate. There, the crowd is also extremely high, and I think it would be a good place to investigate physical interactions. And we know that this is happening every year. And every year there's like this heavy and thick crowds that are rushing through the street of Lyon. And I think these kinds of events with a totally different social context as the one we investigated here are a good ground to study dense crowd. There's also like protests, as you said, but those are epiphenomens that are hard to predict. And I think, our best shot is at regularly happening events. There's also a pilgrimage, which are intensively studied. I don't know if going in this crowd would be very ethical, but we can think of such experiments.
Okay, thank you very much. That's all for my questions. So I have several of them, but we have to end at some point.
Thank you very much, Cécile. And now you will discuss with Armin Seyfried from Germany. Armin.
Thank you. Yeah, thank you. Yeah, Thomas, also from my side, congratulations to this very, very impressive work. And I remember when, when we started the project 4 years ago, and it was really a difficult situation. We had Corona and we had the idea to work on crowds and all these things. So at the end, I believe also for a PhD student, it's difficult to start a project limited in time in such a situation. And I congratulate you for all your achievements and your results. But also my role is to ask the questions and also a little bit a critical question. A lot of motivation we had to study these crowds and this high density and balance was the domino effect. Yeah, that was somehow a trigger that we are interested in that. Now, your work was on balance recovery and not on domino effect appearance. So, but can you give some relations between these two? So why we have, because this domino effect was clearly an end of the possibility to recover balance, and how are your results related with that?
Yeah. So I think the domino effect that has been investigated is one special context. This can be seen, for instance, with the different experimental group information that have been tested during the Wuppertal experiment. So, for instance, when there's like staggerness between individuals, this domino doesn't really represent what's going on, because participants have like one person in front of them, then they have like 2 persons in front of them, then one again, then so it's always more complex than that. But we can imagine a chain of recovery where someone would lean on someone else. But what has been observed in the data, and especially here, if I come back on this slide here, the leaning behavior that we have observed, which correspond to what have been described as being the main effect leading to the domino effect, is that this behavior was only observed for 3 of our participants out of 330 trials. So it only appeared on 3 of them, and it was only happening when no distance was between the participants at the beginning of the experiment. This meant that for every other experiment, when they had the chance to step, participants would not would limit as much as possible the load they would impose on the other individual. They would have physical interaction. This is a fact, because physical interaction propagated in those contexts. However, they would step with the same or even a more conservative way. So they would step they would initiate step in less critical situation in order to not have this behavior of leaning onto others. Mm. So what we have seen here is that the domino effect is almost never happening. To happen, it would require that participants are first like completely stuck to their neighbors, and then that they would have no place to step. And I can really doubt that, but I mean, this can happen. And if they have no place to step, yeah, it will create leaning. And this is when it gets dangerous. And this is why actually we observe, I think, such a few number of leaning strategy is because this is very dangerous. And the domino model, I think, can be used as a last resource model. So when leaning behavior happen and domino effect happen, this is when it gets dangerous, because it means that people cannot recover using step. And so the perturbation, like the intensity of the perturbation is increasing this time because of this domino. So you have all the load of all the participants that are applied on the final person. So I think the human domino is a model that is limited to a very small number of observations. And most of what have been observed during this experiment is that people tend to reduce as much as possible the use of sexual tools.
You have written that also in your conclusion, I remember. Exactly that what you said at the end, but I'm not sure. I have in mind that when we watch these movies for the experiments, there were also some runs where the distance was not, there was no contact, but still a propagation of a push. Have you more insights in that, or what is your opinion on that?
Well, it's difficult. Like I did not study the intensively propagation of perturbation.
Okay. Yeah. No. It's sorry. I know that. So for the future, can you go to page 43 and 44?
40.
One of
so
them.
this is.
Okay, we have it already. No, we have it already. Yeah, you are right. So one conclusion you said was that the steps are shorter in the crowded conditions. That's right?
Yes.
Okay.
So I think it's on the next one here.
Yeah. I'm now like a child. Why? So.
So the dashed line here represents the regression based on forward steps of single individuals. So forward steps are the strategy that have been mainly used in this group context. So we compared here the same recovery strategy. And so what you can see in the, I don't know how to show. Can you see my mouse?
Yeah, I can see your mouse.
Okay. You can see that most data points are below these regressions, meaning that for a given center of mass momentum, which is associated with the perturbation, here participants would have a step length, which is here, rather than single individual would have a step length, which is here. Well above.
Okay, no, I believe on you. I believe you that this is measured. I don't put in question your measurements. I want to know why is it?
Why? Okay. Well, I think this is so the shorter steps are due to the physical constraint, but I mean, it could also be due to the social constraints. Like basically, they doesn't want to step on someone else's foot, so they would use shorter steps. But what is also interesting here is that they use slower steps, which was not seen during the concert event. And I think here it's because they were so it's fully due. Well, not fully due, but mainly due to the social environment. So here they were in a lab, they knew they were gonna be pushed. They have been pushed already many times. And so they were like taking extra care of not stepping on someone else's. And they were also in a social context that would enable us to touch and to make physical contact with others without being socially rude. So they perhaps have used all the environment they could use, so by making contacts or being in contacts directly, and so they could use slower steps in this context because they were not pressed by this physical and this sociological situation for which you want to reduce as much as possible the stepping time in order to unload the person in front of you as quick as possible. So, but this is just an observation, and I'm no expert in social behavior. Here I can only observe that steps were taken slowly, well, slower, like steps were taken with a slower pace than single individuals. And I do think that it's because of the social context.
Yeah, no, I understand. Okay, so it seems a multivariate or multifactorial problem. One last question. In one of your first slide, I believe it was slide number 4, and maybe this question is also connected with Bruno's second question. You said that it's what you did is with this series of experiments, you established an ecological validity.
Yeah.
What is this?
Yeah. So ecological validity is the validity compared to the context. So we embedded our experiments in a context, but this context is associated with a physical environment, but also to a social environment. Like our ecological validity here would be to induce, like to place our experiments in a context, a full ecological context with, so here it was a festival, so you have people cheering, there are maybe some, a good majority of them are in not a sober state. You have, they are here to listen to music. So the ecological validity is a complex intertwinement of parameters that are only visible in very special context. And here, so here it has to be acknowledged that we only study one of this event, and I mean this event will never happen again. Like this festival of this year, with this concert, with these people, was only once. So the ecological variables cannot be replicated. Like it's this is what we wanted to underline with ecological validity. It's like a full set of parameters that are completely linked to crowds.
But I'm a little bit astonished because also I found the first experiment somehow valid and also ecological valid if you take other criteria. Yes. So I'm a little bit, how to say, I'm astonished. Okay, Why is
I do understand. I mean, the context is different. So the ecological validity here is to crowd itself. So we bring our experiments to be closer to crowds themselves. This is a bit linked to the question of Bruno about how can we be sure that we are testing the right parameters? I mean, yeah, it's difficult, and I do agree. I mean, the first experiment also have its full ecological validity in a given context.
That is, I'm fine. With this answer, I very agree with you, Thomas, and I believe that was my last question. Many thanks for the answers.
Thank you.
Thank you, Armin, for questions. Now it is time to conclude with best gazant to supervise a PhD thesis, and perhaps we will begin with Anne-Hélène Olivier, co-supervisor of your PhD work.
Thank you, Bruno. And first, I would like to really warmly thank the jury for agreeing to be here today and their constructive and sometimes provocative question. But I think you really tried to answer to everything in an honest way. So thanks a lot for being here today. And I would like also to thank the participants that are in the room and who agree to be pushed during this year, especially Katia, Alexis, and Solène, who had really great involvement in the Hellfest with the accents on some super warm temperature. And so thanks a lot for that. I won't talk much about the context. I think your director will talk about that. But also maybe thank you also to, as it was said, you can talk a lot. And you really succeed in having this almost 45-minute presentation with the Australian style, so congratulations for that. So maybe because it was questioned in the by Cécile, but I really want to highlight that you really have a huge work regarding the experimentation. I think Thomas really started from scratch related to human experiments. So he was involved in all the process, so the study design, building this stick, pushing stick, and find a good ergonomic way of having this with kind of a reproducible pushed and how to control the angle. You had also the opportunity to discover what is an ethic proposal. And how we should answer to the question with a good administrative thing. So, but you really make it, so it was really great. And you were here for all the data collection, and you did all the analysis. So I think it should be really highlighted because we were just discussing, but you did everything related to the experiments. And you did it with all the rigor regarding experimental data with humans, so I really would like to acknowledge you. And I also would like to highlight that you really want to understand what you are trying to say, and we spend a lot of time on the statistical analysis, logistic regression, so I think it's good that you really try to be curious and really understand what you're doing, so again, congratulations for that. I won't talk too much, but I just want to highlight a few things about maybe your personal way to do. I have to say that Thomas is really proactive in the collaboration, so I think it was also great for the project, especially with Julish. So I think you really link the two labs and really push and be proactive. So I think it's really important as a researcher to be able to work in the team and enjoy working in a team, so I just would like to highlight that, and I think I will let the floor to my other colleagues.
Thank you very much. Ludo, c'est à toi.
So thank you very much for your presentation, Thomas. So I think I will add to the fact that I also saw that it was really clear, it was well structured. We really saw the improvement through the repetition, and I think you provided something like today, a really good talk. I will be brief because I think my contribution to your PhD is also like one of the smallest in the team. Because the topic kind of like went in a way different way of what was originally sold. But I think it was really interesting. I learned a lot, really far from what I usually do. But I hope that I was able to kind of help you in when you most needed it, even though it was actually really far from what I usually do. So in any case, I think it was a really good PhD. It's a pleasure to work with you. You're really organized. I would add to also like I would agree with Anne-Hélène in terms of like your implication in the team, in your application in the project. So it's your rigor, your interest as well in terms of research. So I really hope that you're able to keep going in your research career. That will have maybe the chance to collaborate on other topic, and all the best for the future for you.
Thank you, Julien.
Thank you, Mr. President, and thank you to the award jury for participating in the evaluation of Thomas' work. So yeah, Anne-Hélène mentioned I would give a bit of context. Actually, I think everything has been said, but I will still go through 3 points that I think are important. Indeed, like I think Armin did, it's important to remind that you started your PhD in November 2020, which means that the way it happened, you arrived to the lab, we met, like covered with mask and so on, and I gave you a computer and say, okay, goodbye, see you next year, maybe. And we had all these meetings remotely, and I remember, so we discovered your flat first, before you're even giving you an office, and you were drawing stuff on Windows, equations on Windows. That was a bit weird. I was wondering if maybe there was a crowd of people in your head, and that would be good for dealing with your topic. Okay, so more seriously, yeah, that makes things really difficult to begin with. So it should be noted that you were happy to come back to the lab, but that's important to note that it's a lot of effort to go through this, and you did it successfully. The other difficulty, I think Armin mentioned this, so yeah, related to crowd and in a collaborative project, in this situation was difficult. And like it has been said, I would like to highlight the fact that so you went to Jülich, we didn't ask you to go there, actually, you did this by yourself, you decided to go, participate, collaborate with those people, and I think that the only feedback we got was very positive, and I think it's important to mention this. Field experiments. So I'm not sure we should call it field experiments since it happened in, yeah, there are sort of fields, but they are actually vineyards, so we should call them the vineyards experiments. Yeah, it's a large effort. So I think Cécile mentioned the fact that, yes, you process your data yourself. We can acknowledge that. That's a lot of effort. You went through it sort of smoothly, easily. That was great. But field experiments take even more. Larger effort, small gain. I mean, but you participate the fact that we should go more often to the field because our research is on crowds, and crowds are there. And I'm used now to take this analogy with astronomy. Imagine Galilei working only in a planetarium. So that would not be possible. They started by looking at the stars. They started by building the tools to observe the stars. And I think we should do the same more, way more. And you participate to this effort with no direct gain on what you can say, what you can put in your manuscript. But should be reminded, the effort it takes, I think you died twice in hell, which is a lot in a PhD. So Thomas is probably there, or maybe not, wearing a XN suit. And actually, it's not written on the image, it's 40 degrees outside. And what you see is sort of a smoke, is not smoke on the top. It's actually people throwing at water on the crowd to cool them down. So, yeah, and you were a bit tired after this. And I can understand, of course. So, but yeah, this is part of the effort. This is part of the research effort, and I think this is important to be said. So that's all for my 3 points. Thank you very much for these 3 years. I know that you told me once, je kiffe mon sujet de thèse. Bon, on a kiffé t'encadrer aussi, c'était bien. Thank you.
Thank you, Julien. And the last one, Charles.
Thank you, Bruno. So thanks again to the jury to be here today and to evaluate Thomas. And thanks to my colleague to let me a few things to say, because it's not that easy since I'm the last one. So I fully agree with all the different remarks that have been made, especially about the proactive way you work, the collaborative way you work, and all the effort and the investment you made in this, so to make it work, because it was obviously a big challenge. I will just recall the initial topic we had. In fact, you have done a really great thesis. To me, it's a really good PhD, but it's absolutely not what we planned, and that's kind of fun, because at the beginning we wanted to go from, let's say, simulation of a few individuals to crowd simulation by adding some biomechanical insights into the individuals to the crowds. But the fact is that we said, okay, we need a bit of input, of experimental input for that. And it was a bit, but at the end we have done only that. But that's good. Now we can begin your PhD thesis. That's the good point. So, but it was really interesting also to see that coming from your background. So you are, so people may not know that you are, you have a master in fluid mechanics, in computational fluid mechanics to be exact. So you had to learn a lot with all the work you have done, and you have done it successfully. And we also learn, as everyone said, a lot as well, because to be clear and honest, all of your work was somehow out of our comfort zone, our expertise as well. So we learned a lot from that as well. So for all of that, I think you need to be acknowledged and recognized for all of this work. So I think that all this defense and the questions and the remarks you had during this presentation go in this direction. So I really congratulate you for this work. So that's it. Thank you, President.
Thank you again for world jury. Now we will retire. The jury will leave the conference room and we will deliberate. Then you just have to wait with suspense.
For Armin and Cécile, we need to switch on the other.
Bien, le jury s'est perdu dans la salle. Venez, venez avec moi. Il n'y a plus personne en distanciel, je crois. Comment?
En fait, si on le voit pas là-haut, je ne pense pas. Je sais pas.
Il n'y a plus personne en...
Si je vais aller voir. C'est une bonne idée. Tac. Ça se lance. Ouais, non.
Voilà. C'est pas grave. Bien. Merci d'avoir attendu. Donc, le jury a délibéré et a souligné tout particulièrement, Thomas, la qualité à la fois de la présentation des diapositives, mais aussi du discours que tu as tenu sur ce travail. Nous avons aussi reconnu l'aspect novateur, parce que si tu as utilisé des techniques éculées déjà en biomécanique, les appliquer à l'étude de l'instabilité des foules, c'était un pari risqué, encore plus dans le contexte que tu as pu connaître apparemment, comme nous l'a rappelé Julien. Tu as pu donc t'approprier cette thématique et finalement répondre à la question que tu t'étais posée au départ. Donc tu as su complètement t'approprier ton sujet de thèse. Le jury a aussi noté ta capacité à gérer une collaboration internationale, à mettre en place des expérimentations, à traiter des données, à la fois naturellement ici, mais aussi, si j'ai bien compris, en Allemagne, avec les collaborateurs locaux. Enfin, le jury a particulièrement apprécié la qualité des réponses, puisque tu as, sur tous les champs sur lesquels nous t'avons sollicité, tu as montré que tu maîtrisais les différents aspects dans le contexte de la thèse, mais aussi reconnaissant par là même les limites, parfois, qu'il y avait à tes études. Donc félicitations encore pour cela. Voilà, au final, je crois que maintenant... il est temps d'annoncer qu'au vu de tous ces éléments et d'autres que nous préciserons par la suite, eh bien, le jury a décidé de t'accorder le titre de docteur de l'École nationale supérieure de Rennes. Félicitations.
Ah oui, oui. De toute façon, donc il faut que je fasse le serment
oui, voilà,
du docteur.
Là-dessus, j'en ai copié.
J'en ai une aussi. Donc, en présence de mes pairs, parvenus à l'issue de mon doctorat en... et là, j'ai plus le... C'est automatique, robotique et productique. Et en ayant ainsi pratiqué dans ma quête du savoir l'exercice d'une recherche scientifique et en cultivant la rigueur intellectuelle, la réflexivité éthique et dans le respect des principes de l'intégrité scientifique, Je m'engage pour ce qui dépendra de moi dans la suite de ma carrière professionnelle, quel qu'en soit le secteur ou le domaine d'activité, à maintenir une conduite intègre dans le rapport au savoir, mes méthodes et mes résultats. Voilà. Merci. Donc j'ai préparé des remerciements, mais il y a énormément de monde à remercier. Tout d'abord, j'aimerais remercier tout particulièrement tous les membres du jury. Je suis un peu triste qu'on manque donc les personnes qui étaient connectées en visio. Mais pour les personnes ici, je suis donc très, très heureux de vous avoir ici et d'avoir pu partager donc toutes les questions que vous avez eues. J'ai vraiment apprécié ce moment. Et tant mieux. Et j'espère que ça continuera. Enfin, c'est vraiment à travers les questions qu'en fait on fait évoluer les choses et voilà, c'était vraiment un chouette moment. Je tiens aussi à vous remercier tous les deux. Vous avez été les rapporteurs de mon travail et vous avez passé beaucoup de temps à l'étudier et à vous l'approprier. Et c'est un travail en soi. Et je tenais à souligner ça et à vous remercier pour le travail que vous aviez fourni. Donc voilà, j'aimerais remercier beaucoup d'autres personnes, à commencer par tous mes collègues, donc de l'Inria, du M2S, de l'ENS. Vous êtes toutes et tous ici et ça me touche énormément. On a passé beaucoup de temps juste à vivre ensemble et à travailler sur des problématiques plus ou moins similaires, mais toujours avec une envie du bien faire collectif et je me rappellerai toujours des moments qu'on a passés au repas à refaire le monde par exemple, et aussi des verres qu'on a pu partager ensemble. J'aimerais remercier tous mes amis, ceux qui n'ont pas pu être là aujourd'hui et qui ont peut-être eu la chance de pouvoir me suivre en ligne, mais aussi tous les autres qui m'ont soutenu, tous ceux qui sont dans la salle aujourd'hui, parce que ça fait énormément plaisir. J'en perds mes mots, mais ça me touche énormément. Et voilà, et tous les amis que j'ai pu avoir à Rennes, ça a tellement été essentiel en fait que ça a été constitutif aussi de ma vie ici et ça a apporté énormément aux travaux, même si ça ne transparaît pas dans la recherche, mais sans vous, ça n'aurait pas été possible. Voilà, tout particulièrement, il y a mes amis et il y a les personnes avec qui j'ai vécu au quotidien, donc mes colocs. Et il y a une partie qui est ici aujourd'hui. Du coup, on a partagé le quotidien ensemble et c'est vraiment grâce à vous que je me sentais à Rennes, chez moi. Et c'est vraiment... ça, je l'oublierai jamais. Merci. Après, j'aimerais remercier ma famille. Toute ma famille, mais en particulier mes deux parents. Merci maman et papa. Et merci à Julie et à Pierre. Pierre, il est loin, mais il va arriver bientôt. Mais merci pour tout. Merci pour, pour absolument tout. Je vous dois tout. et je vous aime très fort. Et bah, je suis hyper heureux de partager ce moment avec vous. Et voilà, un dernier mot. Je ne vous ai pas oublié mes encadrants, mes super encadrants. J'ai un petit mot pour chacun d'entre vous. D'abord, je vais commencer par toi, Ludo. Tu as dit que tu avais fait ce que tu avais pu pour t'intégrer à l'encadrement de mon sujet, du coup. Et en fait, je trouve que tu as été parfait, en fait, parce que t'as trouvé ta place et j'ai vraiment ressenti que tout ce que tu me disais m'aidait beaucoup et je suis vraiment heureux que t'aies fait partie de mon encadrement. T'es pertinent, t'es toujours réactif et c'est vraiment un plaisir de travailler avec toi et voilà, je suis très heureux d'avoir travaillé à tes côtés. Julien, sans qui cette thèse n'aurait pas été possible. Ça a été aussi un plaisir. T'es une boîte à idées plus ou moins farfelue, mais toujours, t'es inarrêtable. On trouvera jamais un fond à cette boîte. Merci d'avoir rendu tout possible et d'être la personne vers qui on se tourne pour faire les choses. En fait, c'est Better Call Julien. Ensuite, j'aimerais remercier Charles pour l'écoute et tous les conseils que tu m'as donnés. Vraiment, c'est toi que j'allais voir quand j'étais au plus bas, et c'est toujours toi qui me relevais. Et dans une thèse, il y a des hauts et des bas. Et vraiment, t'as vraiment été salvateur à plusieurs moments. Et je t'en suis extrêmement reconnaissant. Je suis aussi extrêmement reconnaissant de la patience avec laquelle tu réponds à toutes les demandes. Et je me sentais vraiment écouté à tes côtés. Et pour tout ça, j'aimerais te remercier. Et finalement, Anne-Hélène, j'aimerais te remercier pour énormément de choses, mais en fait, je suis aussi admiratif de ton enthousiasme et de ton énergie. T'as vraiment été un phare dans cette thèse, autant au niveau du savoir que de la méthode. C'est vraiment incroyable la façon dont t'es partout, mais tu l'es toujours de façon juste et carrée. Et c'est vraiment, ça a vraiment été un honneur de travailler avec toi. Et tout ça sans jamais perdre le sens de l'humour. Voilà. Donc je suis extrêmement reconnaissant, mais aussi très admiratif. Donc bravo et merci. Voilà. Merci beaucoup. Ouais. Je vous invite tous à venir boire un verre tous ensemble dans la salle Saint. Pour ceux qui ne savent pas où c'est, on va vous y emmener. et voilà, merci beaucoup. Tiens, je sais pas à qui le donner.
Voilà.
Merci. Aïe.
Merci, c'est bien.
Félicitations.
Ouais, allez.